So welcome back to the second lecture of the first week of supersymmetry and conformal field theory. Last time I discussed in very brief detail some reasons why you should care about conformal field theory and conformal symmetry, and also why you should care about supersymmetry. Now the goal of today's lecture is to explain in a little bit more detail what are some interesting aspects of conformal symmetry, why it's a worthwhile field to study, or a worthwhile idea to study on its own right. So why conformal symmetry? So last time I gave you three reasons to care about it. One was critical phenomena, or the theory of phase transitions. One was the renormalization group, and one was string theory. So now let's go through those one by one and try and put on a little bit more meat onto each of those ideas, how conformal symmetry plays an important role for each of these three groups of ideas. So first, critical phenomena. So there are many physical systems which undergo phase transitions. Water is one. You can have liquid, gas, or solid phases of water. I'm actually not interested in any ordinary kind of phase transition here. I'm not interested in what's known as first order phase transitions. I'm interested in a slightly different class of phase transitions called second order ones. This is where the phase transition obeys some kind of smoothness property at the critical point. Whereas in first order phase transitions, there's often a sharp discrete jump in behavior between the two phases. So for the ones that have this smooth transition between the two phases, these systems can have, or often have, or have many times, a conformal symmetry. And not anywhere, but right at that critical point, at, say, the critical temperature at which they undergo this second order phase transition. So let me give you a concrete example of a system which has such behavior. It's a famous system. It's called the Ising model. It has a Hamiltonian, H, which I can write using one real parameter, some kind of coupling parameter J, hopping parameter, sometimes people call it. There's a peculiar sum over the lattice sites of these variables sigma I and sigma j. So it's a lattice model. So you can imagine a square lattice here where you have various lattice sites, and at each of these lattice sites I have one of these sigma variables, which can be plus or minus 1. They're kind of like spins. And they interact to give an energy in this particular way. And I'm only going to sum over nearest neighbors. There's interesting behavior that happens if you consider more complicated kinds of interactions. But for this presentation, we're just going to assume, these two spins could interact because they're nearest neighbors, or these two could interact, but even on the diagonal, they're going to stop interacting because then they're farther apart. Okay, so that's the Hamiltonian. Let's copy it and write it on the next page since I'm out of room. So here's my Hamiltonian again. Now what happens here is that if we think about this system on this lattice as a function of temperature, so when we think about this theory as a function of temperature, there's a high temperature phase where the system is disordered. There's enough energy, kinetic energy if you will, floating around that all the spins flip back and forth, taking any kind of orientation they like. And then the average value of the spin, that's what I mean by these funny brackets. This is an average value or an expectation value. That vanishes. But there's also a low T phase where I don't have that much kinetic energy, and it's favorable for the spins all to line up, and I get an ordered phase where now the average value of the spins is not zero. And there's some critical point between these two phases, some critical temperature associated with that critical point, where sigma first becomes non-zero, or just begins to become equal to non-zero. It's a smooth transition. It's not a sharp transition. It's gradually increases from zero. That's what it means to be second order. And it's at that critical point where the theory is expected to have conformal symmetry. There are fluctuations in the alignment of the spins at all scales at this critical point. And because there's sort of fluctuations at all scales, there's an emergent scale invariance is what we talk about here, emergent scale invariance. And that transformation with respect to scaling, that scaling transformation is an important generator of the conformal group, as we'll discuss in much more detail next week. So this is one example of many. It's a very famous example, but any of these systems where they have an underlying Lorentz or rotational symmetry to start out with. If they then have a second order phase transition, they'll in general have a conformal symmetry as well at their critical point. The next example I want to talk to is more high energy in nature, and you may have discussed a little bit about this already in your quantum field theory module. If you're taking the advanced quantum field theory course, you'll probably learn much more about it this term. So this is the notion of the renormalization group. I should emphasize that in this first week, there's a lot more I could say about all of these things, about phase transitions, about renormalization group, about string theory in a little while. The point here is not to give you all the details. It's to give you a taste of how this subject fits into some larger framework, something I feel like we often do a very poor job with in theoretical physics. And that's why I'm taking the time out to kind of show you some of the larger picture here. I don't really expect you to grasp all the details, but I hope you can kind of try to put the words in the right places and see the relationships a little bit between these, how these relationships between the words should grow, give you kind of large-scale map of what's going on here. Okay, so the renormalization group. So the rules in quantum field theory depend on scale, depend on energy scale. So a famous example of this is quantum chromodynamics, or QCD. It's a theory of quarks and gluons, and let's write a little picture to show you how I think about it, at least in my own head. I hope maybe it will be useful for you as well. So you think about there being some high energy limit of the theory. We often call this the UV or ultraviolet. And there's a flow, a renormalization group flow down to the low energy limit, which we often call the IR or infrared. Just thinking about the energy of photons in the electromagnetic spectrum for comparison. And the rules change for QCD as you go down in energy scale. If you go really high up in energy scale, you have a theory of essentially free quarks and gluons that interact very weakly, if at all, with each other. And if you go down to very low energy, you instead just find bound states. They interact so strongly that all of the quarks and gluons get bound up into larger composite particles with fancy names. They're called mesons and baryons. Examples of baryons are the protons and neutrons that make up the nucleus of the atom. An example of a meson is a pion. That's actually the lightest particle in QCD. So all of these bound states have mass, and that's an important point. Because they all have mass, that means if you go to a low enough energy scale, below the lightest mass particle, the theory is gapped. There's not enough energy to make anything at all. And so the theory becomes kind of trivial or gapped. There's not enough energy to make even a pion, which would be the lightest particle in QCD. So that would be the IR limit of QCD. And in the UV, in contrast, we have, as I already said, a free theory. Okay? So that's what happens. But more to the point in the context of this discussion of conformal symmetry, at these fixed points, the theory is scale invariant, right? You keep going, and then eventually you reach some fixed point where the theory kind of stops flowing, right? You reach the limiting value, where in this limit, in the high energy limit, you find some conformal field theory, which is scale invariant. Or at the IR limit, it's again a fixed point of the flow. There's again some conformal field theory. So these are kind of trivial examples of conformal field theory. So maybe QCD is not the best example of this. So in QCD, the fixed points, the UV and IR fixed points are free or trivial. That's not the generic behavior. The generic behavior in QFT allows for more interesting kinds of behavior. You might find an interacting conformal field theory with lots of massless particles. So if the particles are massless, then in this low energy limit, you still have enough energy to produce them, and there's no reason why they can't continue to interact. So the Ising model, the Ising model at the critical point could be also describe some IR fixed point of some QFT, and that in fact happens. But at any rate, what's the larger picture here? What's the larger picture? So the claim then is that CFTs describe the UV and IR fixed points of relativistic QFTs that have the Poincare symmetry group to start out with. And as such, they're very useful starting points for thinking about QFT more generally. So an almost trivial case in point is the theory of QCD, where a very nice starting point for thinking about QCD is the free limit, where the quarks and gluons are free. And you can look at perturbatively around that, where the interactions are still weak, and try and get some intuition about what happens in QCD in this large energy, high energy limit, UV limit, where the particles are maybe not exactly free, but nearly free. That brings me to the last topic of today's mini lecture, that's string theory. So you may have come away from that discussion of renormalization group with a kind of a bad taste in your mouth. And that's a perfectly rational response to it. RG, as you may have seen last term, and as you'll doubtless see in more detail in the second course on quantum field theory, it comes from dealing with singularities in QFT. This notion of dependence on energy scale. It comes from trying to deal with these infinities that arise in quantum field theory. So where do these infinities come from? Well, QFT is basically a theory of point particles. And the fact that they're points makes them singular. Even the self-energy of a charged point particle is infinite. And there are lots of infinities that come from looking at more complicated kinds of physics as well. The physics of scattering also has similar kinds of infinities associated with the fact that these particles can get very close to each other. So what did quantum field theorists do with these infinities? Well, they subtract them. They introduced counter terms to their Lagrangians and their actions that subtract the divergences. But then this kind of opens up another can of worms, because the infinities are not just simple infinities often. They're infinities that often depend on the energy scale, and then the counterterms have to depend on energy scale, and these counterterms then introduce a scale dependence into the physics. And so you thought you had an electron that had a certain mass, but then you go through this renormalization group procedure and you discover, oh no, the mass actually depends on what energy scale I'm looking at, what kind of process I'm looking at, whether I send in the electron with a very high energy or very low energy, might have a different effective mass that would allow me to examine the process. Now, okay, that's the way it is. Quantum field theory is still an extremely useful framework, but you might very reasonably take a step back and say, I don't like this starting point. Can I get rid of these infinities just by starting with some other framework? So one thing you could look into is theories of extended objects, these objects that don't have vanishing size in all the different dimensions. And one such example is string theory, which is a theory of objects which have at least a length. And these theories of extended objects are often less singular. String theory is certainly less singular. And in fact, string theory has other claims to fame as well, which I hope you'll learn about if you're taking the string theory module. String theory is the leading framework, in my own opinion, not universally shared, for unifying the standard model of particle physics with gravity. And the way this works, in 4 words or less, is that standard model you can think of as open strings, or strings with endpoints, and gravity you can think of as closed strings, or rubber bands. And so by using the same framework of an object which has a length, maybe a length with some endpoints or a length that loops around, you can hope to describe these seemingly very disparate concepts in theoretical physics. Now, where does conformal field theory come in? Well, you have to broaden your perspective a little bit. I said they have a length, which they certainly do. So here's my open string, which has a length, but now they're also going to propagate in time. As they propagate through time, they trace out something people often call the world sheet. And it turns out there is a two-dimensional conformal field theory which lives on the world sheet. And so because of that fact, CFT, especially in 2 dimensions, provides a very important toolkit for doing stringy kinds of computations and calculations. So there, I've given you 3 reasons to care about conformal field theory, and that ends lecture 2. When we come back next time, we'll talk a little bit about reasons to care about supersymmetry as well, and that will end the lectures, the recorded lectures for the first week.